Welcome back to ECE 442-542. Homework number 3, if you are checking right now in class, may not be, I know it's not there. I was interrupted this morning. So it should be there later, hopefully. If you're listening to this after the lecture has been posted, hopefully the homework number 3 will be available. And the topics for that are inverse Z transforms and region of convergence, which is what we will talk more about today. And just as a heads up, exam number 2 is tomorrow. No, it's the Wednesday before spring break. So I know you're all anticipating spring break. I'm anticipating spring break so I can grade your exams. But that's the 8th of March, which is a month after your previous exam. And then we'll have a third exam and a final exam to finish up the semester. And the final exam, I think, is on the last day of the exam period. Today, what I want to do is start with a quiz. Since you're good at quizzes, we just had a quiz, we just had an exam. And it's essentially checking to see where we're at relative to where we stopped before exam number 1, and that is, where is this sequence of signals, x of n, defined in terms of n? Is it one-sided, and is it right-sided or left-sided, or is it two-sided? And we'll see where we are relative to that level of understanding with the quiz. And actually, before you answer, I want to answer in unison. And our answer will be at the count of 3 when we get there, but it will be either a thumbs up, a thumbs down, or a thumbs horizontal. And if you're playing along at home, you can look at yourself in the mirror and to see how you answered. If you can't tell whether your thumb is up or down, when you do, put it somewhere in front of you. And I want you to put it in front of you so that everybody can't see and be influenced by your answer. And then I will see all of these thumbs and be able to tell, hopefully, whether half of the class is in disagreement or whether the whole class or most of the class is in agreement, and that might influence the direction or the explanation that follows. Then we will talk about the importance of the region of convergence via some examples. Then we'll look at some different possible region of convergence patterns. How many region of convergence patterns are there? Do we remember? 3, and that takes more than 2 thumbs, doesn't it? So we need 3 fingers to indicate the number of region of convergence. And there's many different possibilities if we have 2 poles in terms of how those patterns can be oriented or distributed relative to those 2 poles. And then we'll do an inverse Z transform and again talk about the impact of different region of convergences. That's just beautiful. Let's just take a little bit of time. No. So here's an example of a region of convergence. We have a pole at A on the real line. This is the complex Z-plane. The region of convergence is outside of that pole. And I want to know the following. For what values of the argument of that signal in the time domain, x of n, is this x of n defined? Is it right-sided, meaning is little x of n described for values or indices n that are 0, 1, 2, 3? Or is it thumbs down? It's defined for n equal minus 1, minus 2, minus 3. Or is it defined for all values of n? 0, 1, 2, 3, minus 1, minus 2, minus 3. Take 10 seconds to come up with an answer. Did anyone run a 100-yard dash? There are 10 seconds up. Speedster, huh? All right, at the count of 3, I want to see thumbs. Thumbs up means it's right-sided, or for non-negative values of n, that x of n is defined, or has non-zero values. Thumbs down means it's negative indices, n less than 0. And thumbs horizontal means it's true for all n's, plus and minus the integers. 1, 2, 3. This little... For those of you that brought dinner and can't raise up your thumbs, you're teasing me. All right, so it looks like everyone is, or most everyone, was suggesting thumbs up. Why is that? Do you remember? Is there an explanation? Pardon? So that gray circle, well, I'm not going to say anymore, but that gray circle is not the unit circle. That's just the boundary of the region of convergence. But the region of convergence is unbounded. It includes z going off to infinity. And we'll see that that implies that these negative indices on x of n have to not be non-zero. They have to be 0. Otherwise, we would have an unbounded z-transform expression. We'll see that in a little bit. Here's question number 2. Similar diagram, but now just 2 options, up or down. And the question is little x of n, which is a to the n, it's that r value, which is a, r to the n or a to the n, is that expression bounded? If it is, thumbs up. If it's not, thumbs down. And that gray outline circle is not the unit circle. We ready to answer? One. I'm not ready. 1. I'll give you just a little bit more time. I'll count slowly. 2, 3. It's a little unclear which thumbs are where, but they may need to be sideways, actually, because it depends, doesn't it? It really depends on where A is. A could be less than 1. Well, this circle is not the unit circle. I thought I made it clear. So here, I tried to say not the unit circle. So let's say that A is less than 1. Is it bounded or unbounded? If A is less than 1, is your thumb up or down? 1, 2, 3. So this is A greater than 1. Let's say magnitude of A, but A is positive. What did I just say? A is less than 1, didn't I? Okay. I'll try to write what I say. Then it would be this one. If A's magnitude was bigger than 1, then it would be unbounded. the same region of convergence picture. The region of convergence is beyond the pole. But if A lied outside the unit circle, then you would have 2, let's say, squared, 2 to the 4th, 2 to the 5th, because the region of convergence from question 1 said you're looking at a causal or non-negative values for the index n. Question. So this would be, let's say, a waveform. The question was, what is this boundedness referring to? Let's just think of it as a waveform, or you could think of it as the pulse response of a system. And the pulse response of a system would then have a Z transform that had a pole, let's say, that's located at A. But maybe the easiest thing to think about is that this is the Z transform's pole of a time domain waveform. If that's the case, then depending on, here's the it depends, depending on where A is located relative to the unit circle, it will be either unbounded if A is outside the unit circle, and bounded if A is inside, if the pole is inside. Here's a different region of convergence. For what values of n is x of n non-zero? Now the region of convergence is interior to this pole at A. We're not told where the unit circle is. It could be, let's say, anywhere. I want to know when is this waveform defined, for what indices n? Up, down, or horizontal? We ready? Do you see that this picture, region of convergence pattern, is different than this picture? Good. All right. 1, 2, 3. Okay, we all should be pointing down, which we are. This is now left-sided. This is for negative indices, and that's because the region of convergence is interior. It includes z equals 0. So if you think back to the definition of the Z transform, if you had a positive index, or the positive values of n would be z to the -1, z to the -2. That means you're dividing by z's inside the region of convergence. And if you include the origin, it's going unbounded. So you cannot have x defined for positive arguments of n. This would be then a thumbs down or a left-sided sequence. One more. If A is bigger than 1, again, the expression is a to the n. It just depends on, maybe I should say alpha times a to the n. We don't know what the coefficient is. I'll just go ahead and change that. So let's say it's alpha times a to the n with some unknown alpha, since we don't know the scaling. But a is now bigger than 1, and we want to know, is this waveform bounded or unbounded? We ready to vote? So bounded is thumbs up, unbounded is thumbs down. 1, 2, 3. Now remember where the waveform is defined. It's defined for negative indices, and we want A to be bigger than 1. So now we are looking at Z in the expression. It will now be it will be something, let's say 3 times z to the -1. But now z is what? Less. So we're looking at 3z being less than 1 for convergence. We'll see that this one actually was bounded, with a being outside or bigger than 1. And we'll relate that in a little bit to where that region of convergence is relative to the unit circle. But in this case, if a is bigger than 1, where is the unit circle relative to that region of convergence? Does the region of convergence contain the unit circle? Yes. If the region of convergence contains the unit circle, then we have bounded behavior. That's one of the key concepts. So you look at the region of convergence relative to the unit circle for boundedness. But where that waveform is defined, we don't care where the unit circle is to define the indices on X. Is that clear? There's two different questions. Where is X defined for what values of n? And after you answer that, is it bounded or unbounded? Question. So boundedness doesn't necessarily, the question was, is boundedness the same as stability? It doesn't necessarily mean the same thing, because it can if this was an impulse response or the Z transform of an impulse response. But I'm trying to be more general than that and say it could just be a waveform. You will have so what's the difference between boundedness and stability? If you have an impulse response and it has a bounded response, then you have a stable system. If you have a transform that doesn't correspond to a system, it's just a waveform, then it's really not really a stability argument. It's just, is your system stable, or, I'm sorry, is your waveform bounded or not? And bounded is that it's below some m, some constant value. It's bounded. All right, so now let's gain some insight into what's going on by looking at two different Z transforms with the same R value. Let's just look at an R value of 1/2. So now our pole is sitting at 1/2. Suppose for the first case, let's suppose that x sub 1 of n is 1/2 to the n. And let's look at the case where we have a non-causal or negative arguments defining this waveform x sub 1 of n. Or, if you wanted to think about what's going on, x sub 1 at time index -1 is going to be what value? 1/2 inverted, or 2. X sub 1 at -2 is now 1/2 inverted squared, or 1/2 to the -2. That's 4. X sub 1 of -3 is 8. And I think you can start to see what's happening relative to this behavior. Is that behavior bounded? No, it's unbounded. Yes. N corresponds to time. So the question was, where are we starting? Maybe in it. So we are, the problem, so I guess what I would prefer that we look at is infinity is way out there, and when we're at infinity, we're unbounded with our response. and we can't recover from an unbounded response, is sort of one way to think about it. So in this case, it really sort of says, how do we want to evolve time? But I would just suggest, let's just worry about whether our signal is bounded or unbounded as time evolves. And at some point during this evolution of time from minus infinity up to minus 1, you're saying, well, it's coming down. Well, we'll never know where it was, in a sense, at infinity. It was infinite. It was unbounded. So I would prefer to just say, sort of consider yourself going back in time, back to the future, no, back to the past. So we're now going from minus 1 to minus 2 to minus 3, and we're going off, or we're going unbounded. But we can still find the z transform of that expression. Because, why? Because that's how we pick our z. We pick the z so that the argument of our z transform converges or allows our geometric series to have a bounded answer. Meaning, if we look for the z transform of little x sub 1 of z, that's capital X sub 1 of z, which is this sum. In general, it's from minus infinity to infinity, x sub 1 of n, z to the minus n. And we can see from the definition, or from, here's our definition, that we are only defining this waveform for negative arguments of n. Meaning we can throw away everything bigger than 0, or 0 and above. Where now we have 1/2 to the n, that was our x sub 1 of n, z to the minus n. But we may want to, just to make this a little cleaner, we might view this as like 2 to the minus 1 to the n, or 2 to the minus n in terms of its expression. And now we can combine the 2 and the z into one particular factor, or our common ratio. Leading us to then x sub 1 of z is now this sum from minus infinity to minus 1 of 2z to the minus n. Which may be confusing to think about minus exponents, negative arguments of the index, so let's just eliminate that. Suppose we define L to be minus n, so that we can talk about positive values. If that's the case, capital X sub 1 of z now evolves from where? Well, it now goes from L equal 1 to infinity. And we can replace negative n with L, so we now have 2z to the L. And that's this geometric series. It's 2z to the 1, 2z squared, 2z cubed, etc., summed up. And what's the common ratio? We want this sum to be defined or to have a value. So it needs to be bounded. What do we know about the common, what's the common ratio? What's common between the two adjacent terms in this geometric series? What factor? 2z. We're increasing each next term by 2z. So we want that factor, 2z, its magnitude to be less than 1. And then we know that we'll be well behaved. Or if we rearrange this so that we just have the absolute value of z on one side of the equality or inequality, we should see that now, in order for this z transform to exist or to be well behaved or to be bounded, we need the absolute value of z to be, just divide both sides through by a positive 2, and we have the magnitude of z less than 1/2. This is the region in the complex z-plane that allows convergence of this geometric series, and that's why we're calling it the region of convergence. Now we have this disk, and it's inside the pole. The pole is at 1/2. So now we have this disk sitting, our region of convergence, inside the pole at 1/2, and that allows this x sub 1 of z expression to be bounded. And what is that expression? Well, now we can use our strategy from before. We can just start looking at terms. Suppose I make this so that I don't have to keep track of too much. Let me just call that w. So that now I have w to the 1 plus w squared plus w cubed. That's what that infinite sum is saying, based on what we've defined the different terms to be. But I want to somehow find a closed form for that, and now I get to play with this infinite tail. I want my infinite tails to look the same. And they can if I do what to an expression like this? Suppose that I copy this down, and I want my tails to look the same. Maybe the leading terms will be different, but how can I make the tail look the same and maybe do something? Can I scale w1 or x sub 1 of z by something? Or I can divide by w, right? Or I can multiply the left-hand side and the right-hand side by the same, so that now I have 1 plus w squared plus w cubed. And I hope you can see that the tail, starting at w, looks the same in the top and the bottom. So that now if I compare those or take the difference between those, I have 1 times capital X sub 1 of z minus w inverse times capital X sub 1 of z, or 1 minus w inverse x1 of z, and I'm subtracting the blue from the black, and what do I end up on the right-hand side? My tails look the same. The tails of the expression, don't be looking at my tail. But what's on the right-hand side? Subtracting the blue from the black, I get a -1. Or this now allows me to find a closed form expression for capital X sub 1 of z, which is the z transform of that time domain waveform that we began with. Little x sub 1 of n is 1/2 to the n for negative arguments on n. We've now figured out that that geometric series converges as long as the absolute value of z is less than 1/2, and capital X sub 1 of z is -1 over 1 minus w inverse. Or if we multiply by 1, which in this case could be w over w, I have minus w over w minus 1. What? I have z's and w's, but just now go back and remember what w was defined to be. That was 2z. Or we can now finish this up and say that capital X sub 1 of z is now minus w, which was 2z, times 2z minus 1. Or if I factor a 2 out of the numerator and denominator, I end up with minus z over z minus 1/2. That looks familiar, that z minus 1/2, because I had the pole at 1/2. And where is this valid? Where is this z transform defined? What's my region of convergence? We need the absolute value of z less than 1/2. Or if we sketch this, here's the z-plane. We have a pole at 1/2, and if we have our unit circle, that's close enough. But where's the region of convergence? It's the values of z inside a magnitude of 1/2, or it's sitting in here. There's my region of convergence. The red is the unit circle. And let's make some observations relative to this particular example. And note where the shaded is, region, that's the region of convergence, relative to the unit circle. Is the red contained inside the green? The region of convergence, it doesn't lie on top of the region of convergence or within the region, does it? So here are some observations. One is that the time domain waveform, that was little x sub 1 of n, that time, I'll call it a response, time domain response is unbounded. And if it corresponded to a system, that system we would say would be an unstable system. You just told me that the region of convergence does not contain, or the picture told us, the unit circle. Or the unit circle does not lie on the region of convergence. And here is our connection. Because the unit circle is not contained within the region of convergence, we have an unbounded response. And before we could even, or before we even looked or worried about that, we could determine where our x sub 1 of n waveform was defined. That was given to us in this case, but it's relative to the unit circle. I'm sorry, the region of convergence. The region of convergence is interior let me say to all poles and that allows us to conclude that we have a left-sided time sequence. Or x of n is not equal to 0 for n less than 0, and x of n is equal to 0 for non-negative n. That's what we're meaning by left-sided. The left-sided is because the region of convergence is interior to the pole. The bounded behavior or unbounded behavior is because the unit circle is not contained within the region of convergence. Let's look at a second case. Again, using the pole at 1/2, but now let's suppose that x sub 2 of n is equal to 1/2 to the n for non-negative n. So that now we're starting with n equal to 0, having 1/2 to the 0, or 1. 1/2 to the 1 is 1/2. 1/2 to the sub 2 is 1/4, etc. And we just keep going. Now we have this exponential decay. Let's find the z transform of that expression. X sub 2 of z is this sum from n equal minus infinity to infinity of x sub 2 of n, z to the minus n. That's the definition of our z transform. It's only defined for non-negative values of n. We can eliminate then the negative values of n, or we can put the constant and the z terms together into one term, and we can say we're looking at this sum from n equals 0 to infinity of 1 over 2z, z to the minus 1. We'll just put that downstairs, and now we have 1 over 2z to the n. And what's the common factor in this geometric series? What if we took the ratio of two adjacent terms in our series, what would that ratio result in, or what's the common factor? 1 over 2z. And what do we want that common factor to be in order for this expression, this sum, to be well behaved? We need it less than 1, because we're raising that to positive powers. So that now we want this to be well behaved, we need 1 over 2z magnitude to be less than 1, or we need now that the absolute value of z is bigger than 1/2. And what do we know about this expression? If we now call this, let's say that we call this w sub 2, we now have w2 raised to higher and higher non-negative powers. What's the closed form expression in terms of w sub 2 for that? We can do our sequence, multiply it by a particular number, and then divide things out, and we end up with 1 over 1 minus w2. Or replacing what we just defined w2 to be, or writing that maybe in a form that you might have seen it written, and we can multiply by 1, which is z over z, and have z over z minus 1/2. And look at this expression relative to what we had for capital X sub 1 of z. They look very similar, do they not? So if I just gave you that expression without a region of convergence, you wouldn't be able to tell me whether you had a left-sided or a right-sided. You need that region of convergence to actually tell you which of these sequences, time sequences, you have. In this case, the second case, what did we say we needed for z? We needed the absolute value of z to be bigger than 1/2. Or, pictorially, now, this is the, you can't, well, you can see, can you not? Now you know, hopefully, let me draw the picture of where we were. We had a pole at 1/2. And where was our region of convergence? It was values of z. This is the complex z-plane. Our region of convergence was beyond z equal to 1/2. And where's the unit circle? Great. Great unit circle. But where is the unit circle relative to the region of convergence? Now the unit circle is contained within the region of convergence. And what are some observations that we can make in this case relative to this second example? The second example was x sub 2 of n is equal to 1/2 to the n for n greater than or equal to 0. What do you know about that waveform as a function of n? How does it behave? Is it bounded or unbounded? Here, the time domain sequence, x sub 2 of n is bounded. And if we were dealing with that being the pulse response of a system, that would be a stable system. The region of convergence actually contains the unit circle. And that's now our connection with whether our signal is bounded or not. In this case, the fact that the unit circle is lying within the region of convergence, that tells us that we have a bounded waveform. And the fact that we had a right-sided or causal sequence told us something about the region of convergence relative to our poles. Here, the region of convergence is exterior or outside all the poles. Or a right-sided sequence, which says that we now have x sub n not equal to 0 for n non-negative, and x of n is equal to 0 for n less than 0. Question? We're not going back, but go ahead. The question was going back to the left-sided sequence. Yes. So now what's the difference between, the question was in the previous example, little x sub 1 of n, you had the z transform equaling, from memory, capital X sub 1 of z equal to minus z over the denominator z minus 1/2. And we also said that we know the region of convergence there needed to have the magnitude of z less than 1/2. Why did we need that magnitude of z less than 1/2? Where did that come from? What's the region of convergence giving us? That gives us a bounded geometric series, did it not? We forced that on Z so that that sum of terms in that infinite series was bounded. That gave rise to the absolute value of Z being less than 1/2. In this case, what did we need capital or little z to be for our sequence to be bounded? We needed the absolute value of z bigger than 1/2. And that allowed that sequence to sum to a bounded value or a well-behaved number, so that now this particular sequence's z transform, we had capital x sub 2 of z equaling z over z minus 1/2, but this one was for z bigger than 1/2. What capital X of z equal to, if I gave you this expression, and only that expression, could you tell me what little x of n looks like? That's the whole point of this discussion, is if I just give you z over z minus 1/2, can you tell me what the time domain waveform little x of n looks like? You can't without some additional information, and the additional information is the region of convergence. With the region of convergence and this, then you can tell whether the 1/2 to the n is either a left-sided or a right-sided sequence. Meaning, what capital X of z equal to z over z minus 1 corresponds to in the time domain, or what is the inverse z transform of capital X of z, is unclear until somebody tells you where z is defined, or where this expression evaluates to a valid number. In the time domain, to find that depends on the region of convergence. So you need more information. If somebody simply gives you this transform and they don't tell you anything else, if they tell you you have a causal signal, then they're telling you what's happening. You now know the region of convergence is unbounded. You know the region of convergence is beyond all of the poles in your system. If they say it's anti-causal, or the signal is true for negative values of n, then you know that you have a region of convergence inside, interior to all of your poles. Those two pieces of information are required in order for you to inversely transform an expression. The other fact that I want to simply state is the following. The region of convergence never contains any poles. You will not have any poles inside your region of convergence. They're outside of the region of convergence. Let's look at some more interesting examples than just one pole. Let's look at what happens, or different possibilities, for the region of convergence with two different poles. Because I think you already know what you could come up with or cook up for just a one-pole system. Question? Yes, so the function is going to go unbounded at those pole locations, and we now don't want that to happen in our region of convergence. That's one way of sort of thinking about it. We don't want poles in our region of convergence. We want our geometric series to sum to a bounded answer. And that's only going to happen if the poles are nowhere inside the region of convergence, by definition of the region of convergence. The region of convergence is defined so that it does not include any poles. That's how we're defining the region of convergence, which means then that the region of convergence should never contain any poles. Let's look at some possibilities on two different poles. Let's say possibility number one. Suppose that I have a pole at 1/2 and a pole at 3/4, and suppose that my region of convergence is exterior to those two poles. Meaning, this particular point right here is in the region of convergence, and I'm going to let that point go all the way out to infinity. I can let it hit an extreme point. So we could, in our evaluation of this expression, we could say, let's let this point go to infinity in our argument for, is this expression well behaved for all values or points in z in our region of convergence. We could let that z go wherever we want out to infinity. What, in this particular case, well, what's the dominant pole? What do we mean by dominant? Pardon? Okay, the dominant pole is at 3/4. What is meant by the dominant pole? It's the one that's the slowest. It dominates the response, and it's going to be closest to z equal to 1. So our dominant pole is the pole at z equal 3/4, which means if I ask you for the structure of the waveform x, little x of n, corresponding to a system that has these two poles, what would that structure look like? This is an exam 1 question, an easy exam 1 question. I thought it was an easy exam 1 question. It was last week when you were studied up. You did a dump as far as your memory of this material. The final exam is comprehensive. Let me just remind you that you will have to remember, but here, we have something like that. And now what we may not know is, what are the values of n where this is true? Is it left-sided? Is it right-sided? Is it two-sided? Suppose this is now x sub a of n, and this is x sub b of n. Then we could think about x sub b of z as this sum from n equal minus infinity to infinity, x sub b of n, z to the minus n. Or this is now coming up from negative values of little n, and let's just say that we now say that it's x sub b of minus 2, z to the minus 2, plus x sub b of minus 1, z to the minus 1, plus x sub b of 0, z to the minus 0, x sub b of 1, z to the minus 1, etc. Now, we want this expression to be bounded or well behaved for all points in this shaded red region. And now let's just examine what happens for that green point. That's a point in our region of convergence. And let's let that green point go get big, big, big. What happens over here when z gets big? We have z to the what power? We have z squared. What do we know has to be true for little x sub b at -2 if z is going unbounded and we're squaring it? Does that force something to happen to this particular coefficient in that expansion? Do you see that this has to be 0? What about this term? That also has to equal 0. What about every other negative indexed term in that expression? The negative tail. They're a big Z cubed to the 4th, etc. They all have to be 0. So our sequence is right-sided. The only values where little x of n can be non-zero are for non-negative values of the argument. Or we've now, for that pattern of region of convergence, hopefully you can see that little x of n is, let's say, causal. That means if we excited the system, if it was now a pulse response at time 0, it's going to respond at 0, 1, 2. It's not going to do that. It doesn't anticipate. It's not anti-causal. Question. There are anti-causal systems in the real world. That was the question, are there, if you want to think about signal processing or other applications. In a controls class here, we like to think that a system is not going to be anticipatory or anti-causal. So in this class, most of our discussion will deal with causal systems. Ones that when you excite them, they behave. It's not, or they jump around. They don't jump around and then get excited or hit. Right? Unlike some people we might know. Sometimes, never mind. Okay, so now we know x of n is causal, which says that x of n is equal to 0 for all negative n. And this causal really says that our region of convergence is unbounded, or right-sided, meaning x of n is not equal to 0 for n greater than or equal to 0. That's right-sided, or causal, because we have an unbounded region of convergence. What about possibility number 2? For our region of convergence relative to two different poles. Suppose now that our region of convergence is interior to all the poles. If we looked at this, what can we conclude? Now if we looked at, let's say, x sub 2 of z, and let's just consider it for, well, one of those. If we were doing this sum, now we have minus infinity to infinity of x sub 2 of little n z to the minus n. We now have, oh, I don't know why I used x sub little 2, so I'm going to change the notation. That's slow to write. We're coming up from the bottom, x sub 2 of minus 2, z to the minus 2, plus x sub 2 of minus 1, z to the minus minus 1, plus x sub 2 of 0, z to the minus 0, plus x sub 2 of 1, z to the minus 1, plus x sub 2 of 2, z to the minus 2. And this expansion is supposed to be true or well behaved for all values of z. If this region of convergence is the region of convergence, then we could pick a point, any point. A nice point would be really close to the origin or right at the origin. And what's going to happen to that coefficient if 1 over z and z is getting really, really small? What's that term going to do or force on x sub 2 of 1? It's forcing it to equal 0. Do you see that it's also forcing x sub 2 of 2 to equal 0? Because now we're 1 over a small number, 1 over 0. We can't be including those infinite terms for this sum to be well behaved, which says then that for this particular region of convergence that's interior to all of our poles, now we have which terms in our time domain waveform being non-zero? Which indices? Negative or non-negative? Negative. This is now an anti-causal sequence, or we now know that x of n is not equal to 0 for, let's say, n less than 0, and x of n is equal to 0 for n greater than or equal to 0. Maybe I should do this to try to keep it a little bit cleaner. Or this is now what we might call left-sided. Yes? So now, in this case, the question was, why does x sub 2 of 0 have to be 0? It really doesn't if you have a left-sided sequence. But when you have a two-sided sequence, you don't want to count it twice, so we just want one of these to be valid at, let's say, x sub 3 at 0. Let's look at another example for illustration. But this is now okay to be non-zero at n equals 0 if we wanted to. But generally, just to be consistent, we only include that 0 term in one of the sides. And here we'll just consistently put it in the right side so that we're starting our causal sequence at n equals 0. But let's now look at the third possibility. Relative to these two poles. We have a pole at 1/2, and we have a pole at 3/4, and this is really going to test my drawing or sketching abilities. But let's say now here is our region of convergence. It's in between the pole at 1/2 and 3/4. And this is now different from possibility 1 and possibility 2. It's really sort of a combination of those two. If we look at this, where is 3/4, the pole at 3/4, relative to the region of convergence? Is it exterior or interior to the region of convergence? The pole at 3/4 is outside. the region of convergence. And what did we know about poles outside the region of convergence in terms of sidedness? Or maybe I'll start with the other one. Let's start with the pole at 1/2. Where's the region of convergence relative to 1/2? Outside of 1/2, right? And if we looked at just that one, our region of convergence would go unbounded. And what sidedness did we have for unbounded regions of convergence? Right side. Now we want to take that, so we now know that the pole at 1/2 let me just say it's alpha 1, is defined for n greater than or equal to 0. It was the pole, in this case, is interior to the region of convergence. Question? When I'm saying the region of convergence is unbounded, I'm not saying that the response is necessarily unbounded. Is that clear? The region of convergence, so here you have to really pay attention, and hopefully I don't fall asleep and misspeak. But here, the unbounded behavior of your region of convergence is not necessarily the same as the behavior of your time domain waveform. You could have one being unbounded and one being bounded and vice versa. In this case, if we just had the pole at 1/2, the region of convergence is outside it. What if we just had the pole at 3/4? Where is the region of convergence for it? So now cover your eyes or sort of erase the pole at 1/2 and say, oh, where's my region of convergence for the pole at 3/4 relative to the pole at 3/4? It's inside. And what do we know about the sided nature of the regions of convergences inside poles? It's now left-sided, isn't it? So this is true for n less than 0, and this one is with the pole is outside the region of convergence. And so in this case, we actually have x of n is made up of two pieces. One-sided is relative to the 1/2 pole, and the other side, the piece, the left-sided piece, is due to the 3/4. Now what can you tell? So this is now a two-sided sequence, and it's the intersection of the region of convergence outside of 1/2 and the region of convergence inside of 3/4. We need both of those regions of convergences to be true at the same time, so we take their intersection. Because what do we know about the poles? They can't live in the region of convergence. So they are bounding the region of convergence in this case. And what do we know about the shape of this region of convergence that gave rise to a two-sided time domain sequence? It's a donut, or a bagel, or annular. So now the question was, why can't we, I think this is the question, why can we not have a region of convergence, I had to look at the color, that is the following. Is that what you're asking? Because it's ugly, right? Because I can't draw, but it's not connected. So now pretend that you're an ant, a bug, not A-U-N-T, A-N-T, and you tried to move around or get to any points within the region of convergence. It's disconnected. You couldn't get from this inner region of convergence, supposedly, and the outer. A region of convergence has to be connected. The three that we've done, an ant can live in those and get to any points in those three. A donut, a disk, or I don't know what to call it. An unbounded with a hole in the center, right? But we can't have this shape. This is an unallowed cannot be disconnected. So let me try to, and you know what? I needed more space. I wanted to, and I'm playing with fire, but I will anyway. I'll cut my piece of paper and tape it back together. I wanted to say that this two-sided sequence now corresponds to an annular region of convergence. Question? So now the question is this x of n that we've ended up with, is it bounded, is it unbounded, or does it depend? In this particular case, what is it? Let's look at this. If we now looked at the top piece of this, the causal piece, we have 1/2 to the n, where n is non-negative. What's that going to do in terms of a time sequence? Is it bounded or unbounded? The alpha 1, 1/2 to the n. That one's okay, is it not? That one looks okay. This one is bounded. But what's this one doing? 3/4 to the -1, 3/4 to the -2. What's it doing? Now we're basically saying 1 over 3/4 to the 1, 1 over 3/4 squared, 1 over something that's getting tiny, but it's in the denominator. And what's that going to do for us? I'm going off to negative infinity, if you couldn't tell. And I'm now playing by the new clock. Oh, I moved into an unstable region of the room, did I not? Do you see what's happening to this piece? Is it bounded or unbounded? This one's unbounded. And what can we say about the region of convergence here and the unit circle? Where is the unit circle relative to this region of convergence? Is the unit circle inside the region of convergence? No. So we do have an unbounded behavior. But now I want you to go home and start drawing all sorts of possibilities. Do you see that if I move that pole from 3/4 beyond 1, that it would now be a stable or a bounded two-sided sequence if I kept the one pole at 1/2? You can play all night with this, but we will stop at this point, even though I still owe you some time because of other issues. Have a good evening.